Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Brownian motion and its significance. Let's begin. Brownian motion. Brownian, a scientist, he is a botanist. In 1827, botanist Robert Brown observed that pollen grains suspended in water and he viewed under a powerful microscope, and he saw that an irregular continuous dancing motion of these pollen grains throughout that of water surface. Later on extended his observations to the suspensions of a large number of inorganic substances like colloidal solutions that examined under ultramicroscope, and he observed the particles move to and fro rapidly and continuously. The particles of these colloidal solutions are moved to and fro rapidly and continuously in an entirely haphazard manner. This irregular motion is called Brownian motion of particles. This type of irregular motion that he observed by doing such experiment, that type of motion of particles is known as Brownian motion according to the name of Robert Brown. Some examples of Brownian motion like the smoke particles in air. If you observe examples, as smoke particles in air, the smoke particles are motion randomly and haphazardly. That is an example of Brownian motion. Again, if sunlight passes through the door of a house and that house is in dark, and there will be dust particles inside that of sunlight through that of door, the dust particles are in random motions, and this type of random motions of dust particles are observed through our naked eye. That is an example of Brownian motion. There are some facts related to the Brownian motion. Facts related to that Brownian motion. The motions are completely irregular and random. The Brownian motion is completely irregular and random, and the motions are continuous, no discrete, that is continuous, and the smaller particles more lively and noticeable are motions. If the particles are very small, then that type of motions are noticeable to our naked eye, or we can easily notice that type of motion. The motions become more fast with increase of temperature. As we increase the temperature, then the motions are very fast. This is the basic idea of Brownian motion. Now, that Brownian motion is proved by the scientist Sir Albert Einstein. He proposed his theory named as Einstein's theory of Brownian motion to prove how these particles behave such type of motions. He proved that one by using the kinetic theory of gases. So let me discuss how he observed that theory. Einstein's theory of Brownian motion. According to Einstein, the Brownian motion is the best evidence of the existence of thermal motion of atoms and molecules. Is there will be a thermal motion of atoms and molecules? That can be answerable by using Einstein's theory of Brownian motion. There are some assumptions that he taken in consideration to derive the mathematical equations related to Brownian motion or mathematical proof of that Brownian motion. The assumptions are the particles suspended in fluid, here liquid or gas treated as fluid, takes part in thermal motion of molecules of liquid, and these particles are continuously stuck on all sides by the molecules of the fluid. If there will be a fluid or gas molecules are there, and the particles, the suspended particles, let me suspended particles here, that suspended particles continuously stuck in all sides of the molecules on that of fluid. So, these particles are very small in size, the suspended particles here are very small in size, and these particles are continuously hit by the number of molecules on opposite sides. These particles are continuously hit by the molecules of opposite sides, hence they do not always exactly balance due to there will be the stroke of another particles to that of opposite directions. So, they do not exactly in balance, hence each particle experiences an unbalanced force, hence continuously driven about in random directions. Due to that unbalanced force, they continuously driven about its random directions. Thus, these particles behave as molecules of fluid. That is why these particles are behave as the molecules of fluid. These are some assumptions taken by Sir Albert Einstein regarding Brownian motions. And first, he mathematically proved regarding the Brownian motions. So, here he showed that according to Einstein's theory of translational Brownian motion, he observed that in the translational way, translational Brownian motion, what is observation? The particles in due course of time tend to diffuse into medium in account of their random motion. If there will be particles inside that of gas or liquid, what we say, here we take the gas, these particles are diffused into that of medium as you taken in consideration on account of their random motion. Some of the particles are diffused. Due to that diffusion process, the mathematical observation is found as the diffusion coefficient. The diffusion coefficient was determined by Einstein in two different ways. One way, from the irregular random motion of suspended particles, as the suspended particles are irregular and random motions, from this we calculate the diffusion coefficient. And another way to calculate from the difference in osmotic pressure between the different parts due to the difference in concentration of suspended particles. Let here there are so many number of particles. So, the different parts here, the osmotic pressure is not same to that region, there will be the difference in osmotic pressure. So, with the difference in osmotic pressure, the concentration of suspended particles are different, and it is different. According to that difference taken in consideration, we can easily find out the diffusion coefficient. This is the another way to derive the diffusion coefficient. Let me discuss these two different approaches to find out the diffusion coefficient according to Einstein's theory of Brownian motion. Let me calculate calculation of coefficient of diffusion from the random molecular motion. How we calculate? Let the molecular concentration is not uniform. Here we take This is the translational way, translational motion. Length be x, here be the pressure P1 at surface H1, surface S2, the pressure will at P2, N1 in the molecular concentration at the surface H1, N2 with the concentration at the surface H2. This is x axis, this is x axis. So here we take the molecular concentration is not uniform, molecular concentration is not uniform here, molecular concentration is not uniform and has a gradient along x axis causing the diffusion of particles. Due to this gradient of molecular concentration, since molecular concentration is not uniform, so there will be the gradient of molecular concentration. Due to that of molecular concentration, the gradient in molecular concentration, the diffusion of particles along x direction. Let every particle suffers displacement x in time t. Every particle suffers displacement along x axis as x distance in time t. Every particle. Let we consider a cylinder with its axis which is parallel to x axis, and let A be the area, A be the area of cross section of cylinder, area of cross section of cylinder, S1 and S2 are the two end faces of that of cylinder, as we show. S1, S2, the two end faces of cylinder. Let N1 and N2 are the molar concentration at the end faces S1 and S2. N1 is the molar concentration at face S1, N2 with the molar concentration at face S2, and here let N1 is greater than N2, means the molar concentration at face S1 is greater than the molar concentration at face S2. Then what happened? The number of particles crossing the surface S2 to right, means from that surface to this surface, how much number of particles are crossed in time t. We calculated here. Then the number of particles crossing the surface S2 to right in time t is equal to, that is a half, that is the molar concentration at the surface S1, that is N1 displacement x into area of the cross section A. This number of particles are passes through that of surface S2 from right. Again, how much number of particles passes through that of surface S1 to that of left? as we take the total number of particles be n and half of the particles moving towards right and half of the particles moving towards left. It should be noted that half of the particles contained in that of cylinder moves towards right, whereas the half of the particles moves towards right. Here we take that, noted that half of the particles moves towards right and another half moves towards left inside the cylinder. So here is the number of particles crossing the surface S2 to right in time t. Again, similar manner we can calculate similarly number of particles crossing the surface S1 crossing the surface S1 to left in time t, will be half number of that is the molar concentration N2, distance x, area A. Here half N1x, the number of particles passes through that of surface S2, and half N2x is the number of particles passes through that of surface S1. Now, how much excess of particles crossing the middle layer of the right, middle layer to right and middle layer to left, we have to calculate here. Excess of particles, therefore excess of particles crossing the middle layer to the right will be the difference, that is half N1xa minus half N2xa, half N1 minus N2 taking common as xa, the excess of particles crossing the middle layer of that to that of right. Now, let us take the gradient of molecular concentration. Let us take gradient of molecular concentration is equal to minus dN by dx. As it proceeds, the molecular concentration gradually decreases. That is why the gradient of molecular concentration be minus dN by dx. According to the definition of diffusion coefficient, according to use that of molecular concentration, according to the definition of diffusion coefficient, the excess of particles crossing the middle layer to right, the excess of particle crossing the middle layer to the right, that is minus d, that is the diffusion coefficient potential gradient, that is the molar concentration gradient, dN by dx, time into area. This number of particles crossing the middle layer to the right. Here this number of particles crossing the middle layer to right, here the number of particles crossing the middle layer to right. So from these two equations, here I take equation 1 and equation 2, these two be the same. Therefore from equation 1 and 2 we get, means we just equate these two, means half n1 minus n2 x a is equal to minus d dN by dx t into a. Here n1 minus n2 is, here we take n1 minus n2, the difference in the concentration is nothing, that is minus x concentration gradient dN by dx with the change in molar concentration, that is putted here. We have minus half x square a dN by dx is equal to minus d t a dN by dx. dN by dx a should be cancelled with each other. So here we have half x square is equal to minus d into t. So d is equal to, here we have d minus minus cancel out, so d is equal to x square divided by 2t, that is the expression, the diffusion coefficient we calculated here, that is x square by 2t. X with the distance of that of cylinder, t with the time taken. So the diffusion coefficient will be x square divided by 2t. This is the calculation of diffusion coefficient. This is the calculation of diffusion coefficient as we take random molecular motion, means the point 1. Next we have to calculate the diffusion coefficient taking as point number 2. So here taking the point number 2, the diffusion coefficient will be how much? Point number 2, calculation of coefficient of diffusion from difference in osmotic pressure between the different parts due to the difference in concentration of suspended particles. Here we taking consideration as the osmotic pressure. Let again S1 and S2 are the two surfaces of that of cylinder. Here in that of cylindrical way, let pressure P1 and P2 be the osmotic pressure. So we write here P1 with the osmotic pressure on end phase S1 and P2 with the osmotic pressure on end phase S2. Again similar way, N1 and N2 are the molar concentration on their end phases as S1 and S2 respectively. Here N1 with the molar concentration on end phase S1 and N2 with the molar concentration on end phase S2. According to gas law, P1 is equal to N1 kT, where K be the Boltzmann constant, T be the absolute temperature. Similarly, P2, that is N2 KT. Therefore, the pressure difference, pressure difference that is P1 minus P2 is equal to N1 minus N2 KT, that is the pressure difference. Now, due to that pressure difference, the force difference by the cylinder due to this pressure difference, the force difference observed due to that of pressure difference, force difference by the cylinder due to this pressure difference. The force difference, let F, due to that of pressure difference, so pressure into area, so pressure difference P1 minus P2 into area A. Therefore, F is equal to pressure difference, that is N1 minus N2 KT A. This force will push the cylinder in the positive x direction. This force push the cylinder in the positive x direction, Let the mean concentration of the molecule, N1 is the concentration at the phase S1 and N2 is the concentration at phase S2, but the mean concentration, let the small n. Let the mean concentration of molecules is equal to small n, and then the number of particles in that of cylinder, then the total number of particles, in the cylinder, the total number of particles capital N will be how much? That is the mean concentration N, area of the cross section A into displacement x. N is equal to small n A into x. This is the total number of particles inside the cylinder. This force will act on the total particles on that of cylinder as that force exerted due to that of pressure difference. So, this force will act on the particles in the cylinder. Therefore, force acting on the particle, force acting on the particles is equal to, that is the total force divided by the total number of particles on a particle. Force acting on a particle, let that force will be let small f, means total force divided by total number of particles. Total force, that is N1 minus N2 K T A divided by total number of particles, that is N A x, or small f is equal to kt by small n, that is n1 minus n2 divided by x. Here a cancel out. This is the force acting on a particle, and instead of n1 minus n2 divided by x, we can write, as we know, n1 minus n2 is equal to minus x dn by dx. Therefore, or f is equal to kt by n dn by dx. This is the force kt by n dn by dx, force acting on a particle. Now, if we assume the particles is a sphere, let here we write, if we assume the particles as a sphere moving with a constant velocity small v in viscous medium, then according to Stokes law, again the force acted upon each particles will be 6 pi eta r v. Look here, we assume the particles just like sphere. We take the particles just like sphere. The sphere have the radius r, and that sphere move through that of viscous medium with the velocity v. Therefore, the force exerted on each particle will be 6 pi eta rho v, where eta will be the coefficient of viscosity. Look at that equation and that equation. Let I take equation number 3 here, equation number 4 here. This is the force on each particle, that is the force on each particle. Now comparing these two equations, what we have from equation 3 and 4, from equation 3 and 4, we get, just equating these two, so write 6 pi eta r v is equal to minus kt by n dn by dx. Therefore, n v is equal to minus kt by 6 pi eta r dn by dx. What exactly that equation indicates? This equation represents the number of particles moving towards right per unit area. That is, that equation indicates, it represents the number of particles moving towards right per unit area, as you consider in that of cylinder. So, according to definition of diffusion coefficient, according to the definition of diffusion coefficient, means NV, that is the number of particles moving towards the right, NV n into V will be minus d diffusion coefficient into dN by dx, and the molar concentration gradient. Here the equation number V, Vi, these two equations are same. So comparing these two, we can write from V and Vwi, from equation V and Vi we get minus d dN by dx is equal to minus kt divided by 6 pi eta r dN by dx, or d is equal to kt divided by 6 pi eta r. As you know, Boltzmann constant is the ratio of r divided by n, r be the gas constant, n be the Avogadro's number, n is the Avogadro's number. So the equation further written as d is equal to RT by n 1 by 6 pi eta r, that is the diffusion coefficient. D is equal to RT by n 1 by 6 pi eta r. Now from first equation we get d is equal to x square by 2t. What do we know? We know diffusion coefficient d is equal to x square by 2t, which implies x square is equal to 2 dt. Now we have x square is equal to, the value of d is put here, so 2 t RT by n 1 divided by 6 pi eta r. Now x square is equal to RT by n t divided by 3 pi eta r. This is the another expression for that of distance x is calculated here. So here we calculate the diffusion coefficient by using the second one, means due to the difference in osmotic pressure. So what we studied here throughout that of video lecture, we studied about the Brownian motion, facts related to that Brownian motion, and Einstein's theory of Brownian motion, how Einstein proved the Brownian motion by taking the translational Brownian motion in consideration, using these two things to determine the diffusion coefficient. From first one, taking the random motion of molecular motion, molecular motion, mathematically derive the diffusion coefficient, and taking the second one, difference in osmotic pressure, so he calculated the diffusion coefficient taking the osmotic pressure and derive the diffusion coefficient, and from first equation comparing these two we can calculate x square will be that much. So with this useful and informative notes, let me wind up this session. Thank you.